A differential equation is a mathematical equation that relates some function of one or more variables with its derivatives. Differential equations arise whenever a deterministic relation involving some continuously varying quantities and their rates of change in space and/or time is known or postulated. Because such relations are extremely common, differential equations play a prominent role in many disciplines including engineering, physics, economics, and biology. Differential equations are mathematically studied from several different perspectives, mostly concerned with their solutions the set of functions that satisfy the equation. Only the simplest differential equations are solvable by explicit formulas. However, some properties of solutions of a given differential equation may be determined without finding their exact form. If a self-contained formula for the solution is not available, the solution may be numerically approximated using computers. The theory of dynamical systems puts emphasis on qualitative analysis of systems described by differential equations, while many numerical methods have been developed to determine solutions with a given degree of accuracy. For example, in classical mechanics, the motion of a body is described by its position and velocity as the time value varies. Newton's laws allow one to express these variables dynamically as a differential equation for the unknown position of the body as a function of time. In some cases, this differential equation may be solved explicitly. An example of modeling a real-world problem using differential equations is the determination of the velocity of a ball falling through the air, considering only gravity and air resistance. The ball's acceleration towards the ground is the acceleration due to gravity minus the acceleration due to air resistance. Gravity is considered constant, and air resistance may be modeled as proportional to the ball's velocity. This means that the ball's acceleration, which is a derivative of its velocity, depends on the velocity. Finding the velocity as a function of time involves solving a differential equation and verifying its validity. Directions of study. The study of differential equations is a wide field in pure and applied mathematics, physics, and engineering. All of these disciplines are concerned with the properties of differential equations of various types. Pure mathematics focuses on the existence and uniqueness of solutions, while applied mathematics emphasizes the rigorous justification of the methods for approximating solutions. Differential equations play an important role in modeling virtually every physical, technical, or biological process, from celestial motion, to bridge design, to interactions between neurons. Differential equations such as those used to solve real-life problems may not necessarily be directly solvable, that is, do not have closed-form solutions. Instead, solutions can be approximated using numerical methods. Mathematicians also study weak solutions, which are types of solutions that do not have to be differentiable everywhere. This extension is often necessary for solutions to exist. The study of the stability of solutions of differential equations is known as stability theory. Nomenclature. The theory of differential equations is well developed and the methods used to study them vary significantly with the type of the equation. Ordinary and partial. An ordinary differential equation is a differential equation in which the unknown function is a function of a single independent variable. In the simplest form, the unknown function is a real or complex-valued function, but more generally, it may be vector-valued or matrix-valued. This corresponds to considering a system of ordinary differential equations for a single function. Ordinary differential equations are further classified according to the order of the highest derivative of the dependent variable with respect to the independent variable appearing in the equation. The most important cases for applications are first-order and second-order differential equations. For example, Bessel's differential equation, in which y is the dependent variable, is a second-order differential equation. In the classical literature, a distinction is also made between differential equations explicitly solved with respect to the highest derivative and differential equations in an implicit form. Also important is the degree, or power, of the highest derivative, s, in the equation. A differential equation is called a nonlinear differential equation if its degree is not 1. A partial differential equation is a differential equation in which the unknown function is a function of multiple independent variables and the equation involves its partial derivatives. The order is defined similarly to the case of ordinary differential equations, but further classification into elliptic, hyperbolic, and parabolic equations, especially for second-order linear equations, is of utmost importance. Some partial differential equations do not fall into any of these categories over the whole domain of the independent variables and they are said to be of mixed type. Linear and nonlinear, both ordinary and partial differential equations are broadly classified as linear and nonlinear. A differential equation is linear if the unknown function and its derivatives appear to the power 1 and nonlinear otherwise. The characteristic property of linear equations is that their solutions form an affine subspace of an appropriate function space, which results in much more developed theory of linear differential equations. Homogeneous linear differential equations are a further subclass for which the space of solutions is a linear subspace, that is, the sum of any set of solutions or multiples of solutions is also a solution. The coefficients of the unknown function and its derivatives in a linear differential equation are allowed to be functions of the independent variable or variables. If these coefficients are constants, then one speaks of a constant coefficient linear differential equation. There are very few methods of solving nonlinear differential equations exactly. Those that are known typically depend on the equation having particular symmetries. Nonlinear differential equations can exhibit very complicated behavior over extended time intervals, characteristic of chaos. Even the fundamental questions of existence, uniqueness, and extendability of solutions for nonlinear differential equations, and well-posedness of initial and boundary value problems for nonlinear PDEs are hard problems, and their resolution in special cases is considered to be a significant advance in the mathematical theory. However, if the differential equation is a correctly formulated representation of a meaningful physical process, then one expects it to have a solution. Linear differential equations frequently appear as approximations to nonlinear equations. These approximations are only valid under restricted conditions. For example, the harmonic oscillator equation is an approximation to the nonlinear pendulum equation that is valid for small amplitude oscillations. Examples: in the first group of examples, let U be an unknown function of x, and C and I permil unknown constants. Inhomogeneous first-order linear constant coefficient ordinary differential equation. Homogeneous second-order linear ordinary differential equation. Homogeneous second-order linear constant coefficient ordinary differential equation describing the harmonic oscillator. Inhomogeneous first-order nonlinear ordinary differential equation. Second-order nonlinear ordinary differential equation describing the motion of a pendulum of length L. In the next group of examples, the unknown function U depends on two variables x and t or x and y. Homogeneous first-order linear partial differential equation. Homogeneous second-order linear constant coefficient partial differential equation of elliptic type, the Laplace equation. Third-order nonlinear partial differential equation, the Korteweg-de Vries equation. Related concepts: a delayed differential equation is an equation for a function of a single variable, usually called time, in which the derivative of the function at a certain time is given in terms of the values of the function at earlier times. A stochastic differential equation is an equation in which the unknown quantity is a stochastic process and the equation involves some known stochastic processes, for example, the Wiener process in the case of diffusion equations. A differential algebraic equation is a differential equation comprising differential and algebraic terms, given in implicit form. Connection to difference equations. The theory of differential equations is closely related to the theory of difference equations, in which the coordinates assume only discrete values, and the relationship involves values of the unknown function or functions and values at nearby coordinates. Many methods to compute numerical solutions of differential equations or study the properties of differential equations involve approximation of the solution of a differential equation by the solution of a corresponding difference equation. Universality of mathematical description. Many fundamental laws of physics and chemistry can be formulated as differential equations. In biology and economics, differential equations are used to model the behavior of complex systems. The mathematical theory of differential equations first developed together with the sciences where the equations had originated and where the results found application. However, diverse problems, sometimes originating in quite distinct scientific fields, may give rise to identical differential equations. Whenever this happens, mathematical theory behind the equations can be viewed as a unifying principle behind diverse phenomena. As an example, consider propagation of light and sound in the atmosphere, and of waves on the surface of a pond. All of them may be described by the same second-order partial differential equation, the wave equation, which allows us to think of light and sound as forms of waves, much like familiar waves in the water. Conduction of heat, the theory of which was developed by Joseph Fourier, is governed by another second-order partial differential equation, the heat equation. It turns out that many diffusion processes, while seemingly different, are described by the same equation. The Blacker-Scholes equation in finance is, for instance, related to the heat equation. Notable differential equations. Biology, the Hulst equation a biological population growth, von Bertalanffy model a biological individual growth, Lotka Volterra equations a biological population dynamics, replicator dynamics a found in theoretical biology, Hodgkin a Huxley model a neural action potentials, economics, the Blacker-Scholes PDE, exogenous growth model, Malthusian growth model, the Vidalia Wolf advertising model, see also, complex differential equation, exact differential equation, integral equations, numerical methods, Picardo-Lindell paragraph F theorem on existence and uniqueness of solutions, recurrence relation, also known as difference equation, references P. Abbott and H. Neal, Teach Yourself Calculus. 2003 pages 266 to 277, P. Blanchard, R. L. Devaney, G. R. Hall, Differential Equations, Thompson, 2006, E. A. Coddington and N. Levinson, Theory of Ordinary Differential Equations, McGraw-Hill, 1955, E. L. Inc., Ordinary Differential Equations, Dover Publications, 1956, W. Johnson, A Treatise on Ordinary and Partial Differential Equations, John Wiley & Sons, 1913, in University of Michigan Historical Math Collection, A. D. Polyanin and B. F. Zaitsev, Handbook of Exact Solutions for Ordinary Differential Equations, Chapman and Hall CRC Press, Boca Raton. 2003. ISBN 1-58488-297-2. R. I. Porter, Further Elementary Analysis, 1978, Chapter 19 Differential Equations, Teschl, Gerald. Ordinary Differential Equations and Dynamical Systems. Providence, American Mathematical Society. ISBN A978-0-8218-8328-0. D. Zwillinger, Handbook of Differential Equations, Academic Press, Boston, 1997. External links, Lectures on Differential Equations MIT OpenCourseWare videos, online notes/differential equations Paul Dawkins, Lamar University, Differential Equations, SOS Mathematics, Differential Equation Solver Java Player tool used to solve differential equations. Introduction to Modeling via Differential Equations Introduction to Modeling by Means of Differential Equations, with critical remarks. Mathematical Assistant on Web Symbolic ODE tool, using maxima, exact solutions of ordinary differential equations, collection of ODE and DAE models of physical systems MATLAB models, notes on DiffyQS, Differential Equations for Engineers an introductory textbook on differential equations by Jiří Leblev UIUC, Khan Academy video playlist on differential equations topics covered in a first-year course in differential equations. Math Discuss video playlist on differential equations.